And let me go down like this. Okay, hang on. Okay, another thing I want to say before we start, guys. Everybody look at the lab experiment number 1. Okay, watch the video and also learn Circuit Wizard, or if you don't like Circuit Wizard, okay, go and download the multi-sim. And somebody will say, you know what, I want to use all circuit or something like that. But you know, Circuit Wizard, the easy one, but you have to pay, I think, premium for it. Also, the most important thing is when you send me a file on Teams, whether it is homework, quiz, exam, or anything, it should be in PDF format. Everybody get that? PDF format. And it should be written in blue, your handwriting. Okay? Okay, your handwriting will be in blue pen. Okay, blue pen. Okay, that's your handwriting. I don't accept it, you know, to be printed. No print. Okay, no black. Should be blue. Okay, and the file should be PDF file. Any questions? Okay. Everybody see the slides? Okay, do you guys see the slides?
Yes.
Okay. We are on slide number 20 last time, right? Or, right, we are on slide number 20, okay. We are on slide number 20, last time we left. And slide number 20, this is example, and it is part of your homework as well, okay? So we're going to solve it, we're going to go over it. Okay, you can see this, that the circuit here is we have a circuit divider like that, okay, formed by 10K and 20K, like that. And then I have a diode, and then connected to the diode, I have 20K ohm to the ground, okay? Now, over here, this is 3.1. This is a non-ideal diode, or another way, we call it commercial diode, okay, commercial diode. And since we are dealing with commercial diode, okay, the voltage drop across the diode will be 0.7 volts since it is silicon diode, okay, since it is silicon diode. If it is germanium, it will be 0.3, VD will be 0.3, and if it is gallium arsenide, will be 1.2 volt, okay? All right, so when we have a circuit like this, can somebody switch the microphone off, please? Okay, somebody switch it off, please. Okay. Okay, remember that if you have something like this, okay, circuit divider at the input like that, okay, you will see this not only, you know, in here where we are using diode, but you will see it when we are using transistor and when we are using FET transistor, okay, BJT transistor and FET transistor. They will, you will see this network at the input here, okay? Okay, every time you see something like this, the first thing you're going to do is to apply Thevenin theorem to the input here, okay? Thevenin theorem. How are you going to apply it? Everybody remember what Thevenin equivalent? Okay, Thevenin, okay, said, okay, you have to find RTH, and then you have to find VTH. Okay, you have to find RTH and you have to find VTH. How are you going to find RTH? Okay, Thevenin said if you want to find RTH, you could put all the VCC to ground, connected to ground. And if you have current supply, the current supply will be open circuit. So if we put this one here to ground, you will see that R1, which is 10K, will be in parallel with 20K. Therefore, RTH will be 10 multiplied by 20K divided by the sum. And that will give you 6.67K. Everybody see that? Everybody see that? Okay, very good. Now, to find VTH, we put back the volt supply, which is 9 volt, and then the VTH will be at this node here. Okay, so to find VTH, we use VDR, and VDR is equal to what? 9 multiplied by 20K divided by the sum, which is 10K plus 20K, 30K, and that will give you 6 volt. Okay, is there any questions? All right. Now, having found RTH and VTH, now we're going to redraw the circuit. Remember that every time you see a diode, commercial diode in a circuit, you replace it with its equivalent circuit or equivalent model. Okay, and this is shown in slide number, the next slide. Okay, over here. Okay, so this is the original one. I replaced the diode with its equivalent model, which is 0.7 volt. Okay, this is VD. Okay, and then now I'm going to replace this voltage divider network into this here 6 volt, which is VTH, and RTH, which is 6.67 K ohm. Okay, now I have this. I can take KVL over here. Okay, why? Because I want to find I. Okay, I want to find I. So when I can find I, it's like this. Okay, I will say KVL minus 6, okay, plus I multiplied by 6.67K plus 0.7 plus I multiplied by 20K. Okay, solve that. Okay, and it is equal to what? I, you will find it is equal to 0.199 milliamp. Okay, so if I found I is equal to 0.99 milliamp. Now I can find V out. Okay, V out, I use Ohm's law, is equal to what? The current I multiplied by 20K, and that will give you 3.975 volt. Okay, very easy question. Okay, provide that you know how to start. Okay, by converting the voltage divider network into Thevenin RTH and Thevenin VTH. Any questions? All right. Okay, coming back to our diode, which is the junction diode. Okay, and we're going to look at the characteristic of it in a little bit more detail. Okay, so I have ID over VD. Okay, and I have the forward bias and reverse bias. Let's look at the forward bias, and this is, hey you guys, this is commercial. Okay guys, this is not ideal. Okay, this is commercial. Okay, and this is a commercial silicon diode, as I said here, silicon. Okay, now over here, forward bias. How are we going to forward bias the diode? You put positive here, and of course, you know, either negative or 0 here, and therefore the diode will be forward bias. Remember that the forward bias, the diode, you have to exceed 0.7 volt. You have to reach 0.7 volt or more. Okay, so that the diode will be on. Below 0.7 volt, the diode is off or for reverse bias. Okay, as you can see here, the graph or the curve is exponential curve. Okay, exponential. What does that mean? It means, it is subjected to e to the power something. Okay, e to the power something. All right. All right. So if we're going to look at the forward bias, that's in slide number on slide number 23. As you can see, this is forward bias condition. Okay, the current ID is approximated by this formula. This is, for a curve that is exponential. We use this is for any curve that is exponential. We use this formula usually, and it is given by IS multiplied by e to the power v, where v is VD, which is the VD across the diode. Okay, where is it? Is over here, for example. This one here is VD, okay, which is there. See this V? We usually call it VD. Okay, everybody get that? All right. Okay, divided by NVT, where N is constant, and V. Everybody knows what VT is. Capital VT. This is, what is it? This is thermal voltage, which is equal to 25.9 or 25.8 millivolt. Okay, and some of the book, our book uses 25 millivolt. Most of the book they are using what VT equal to 26 millivolt. Okay, -1. So this is the formula that approximates the current in the forward bias condition. Okay, for the diode. Okay, now remember that VT, if you want to calculate VT really, which is equal to K multiplied by T over Q, where K, we call this Boltzmann constant, and it is equal to 1.38 times 10 to the power minus 23. And T is the absolute temperature, okay? And Q, of course, this is the electron charge, okay, for the for either electrons or for the holes, okay, and it is equal to 1.602 times 10 to the power 19 coulombs, and then N is constant. N is constant, is either 1, okay, is between 1 and 2, okay, guys. All right. Usually, if we don't mention, if the question didn't mention N, then regard N as equal to 1. Okay, everybody get that? If the book or the question didn't mention any N, then you regard it as equal to 1. All right, and IS in this case called scared current or saturation current. Okay, that is set by the diode size, or usually it is set by the manufacturer who manufactures that diode. Okay, where do you find that information? You find it in the data sheet of the diode. Okay, and sometimes they call it spec sheet. Okay, specification sheet or short spec sheet. Okay, all right. Now, the equation here, so remember that I is greater than IS, very much greater than IS, okay? Very much greater than IS, okay? And therefore, this one here, this formula here, is approximated like this, to this, okay? Because this one here will be small, okay? Because, if you multiply this by here and here, okay, IS is very small, therefore, the whole thing is reduced to ID is equal to IS e to the power, okay, V divided by NVT, where V is VD. And it is under a red rectangular. When I put something under red, it means it is very, very hot. Okay, that means it is very important. Everybody get that? So whatever you do, okay, don't forget this. Okay, don't forget that. Okay, and suppose I want to calculate VD. Okay, suppose I want to calculate V, which is VD, for the transistor. How am I going to do that? Okay, well, I'm going to do that is like this. Remember that I is equal to Is e to the power V divided by N VT. If I take this Is, take it to the other side, okay, it will be I divided by Is equal to E to the power VD divided by NVT. Okay, all right. Okay, now if I take natural logarithm on both sides, okay, I will get what? V divided by NVT equal natural logarithm ln I, okay, which is ID divided by Is. Therefore, I can calculate V, which is equal to NVT ln I, which is the current ID divided by Is. And it is also under red rectangular. Very important, okay? Very important. So don't forget these, guys. Whatever you do not forget these two formulas. Any questions? All right, very good. Now let's go to the reverse. When we look at the graph of ID versus VD, and we look at the reverse, okay, we see this is the reverse current. Okay, this is the reverse current. This is a micro amp or a nano amp. Okay, now the reverse voltage is negative. Okay, it's negative. This is the reverse voltage. Now you cannot put a big reverse voltage here, okay, because it cannot go forever. There is a point at which the diode will break down if you do, because the diode doesn't like to be reversed or hard. Okay, doesn't like it, because if you do that, then the diode will break. How? The manufacturer, okay, well, the manufacturer, when you look at the specific spec sheet or data sheet, you will see that the manufacturer will say VZK, which is they call it Zener breakdown. Okay, Zener. Okay, they said VZK, which is minus. Well, he will put a value here for it. He said, you know, whatever you do, don't exceed this value. Okay, don't exceed. Don't. I mean, this is the limit. After this, after you exceed this limit, then you will see a lot of current flowing through the diode. Okay, so for example, you know, if you read a spec sheet of a diode that you bought from the store, and you will see that VZK is equal to, say, minus 20 volt. Okay, so you know that, you know, minus 20 volts, that's your limit. Otherwise, the diode, you know, if you exceed it, will break down, and then you will throw your diode and buy another one. Okay, got it? All right. Okay, so when it is reverse bias, ID is equal to Is minus Is, of course, right? Which is the reverse bias current. Okay, and in the breakdown, okay, when the diode breakdown, we will see, you know, that the current is increases rapidly, as shown in the in here, in the IV VD characteristic of the diode. Okay, if you reach, hey you guys, if you just before you reach VZK, the value, okay, you realize that, oh well, you know, wait a minute, I read the data sheet. Okay, I'm not going to go there any further, so I'm going to go back. So you reduce the VZK, or you reduce the reverse voltage, then you know the diode will be saved. Okay, the diode will be saved. Otherwise, you know, if you exceed it, okay, the diode might be destroyed. most likely it will be destroyed. Okay, guys? Any questions? Okay. Now, here is a question, okay, or example, okay, for the diode using the formula we just mentioned. Okay, I said a silicon diode is said to be 1 milliamp device, okay, 1 milliamp, okay, which is 1 multiplied by 10 to the power minus 3, okay, display a forward voltage of 0.7 volt. So this device, when it is 1 milliamp, its VD will be 0.7 volt. So this one is actually silicon diode, okay? And of course, at a current of 1 milliamp, which is the ID, okay? And he wants us to evaluate scaling constant IS, okay? He wants us to find IS and the event that N is either 1 or 2. So he wants us to find IS when N is equal to 1, and he wants us to find IS when it is equal to, when N is equal to 2, okay? And he will say, what scaling constant, okay, would apply, okay, to a 1 amp diode of the same manufacturer that conduct current of 1 amp at VD equal to 0.7 volt. And he said, use VT equal to 25 millivolt. Okay, VD is equal to, or VT, sorry, VT is equal to 25 volt. Remember that we have ID is equal to IS e to the power V, okay, divided by NVT. Okay, now I want to solve for IS. Therefore, IS is equal to I, E, okay. I take this, divide I by E, V, divided by NVT, which is over here. And then I will take this up. When I take it up, this one here will be minus, and that's why it is minus, okay, guys? Okay, therefore, IS is equal to I, E to the power minus VD divided by NVT, okay? Now, for 1 milliamp diode, okay, 1 milliamp diode, I'm going to use N equal to 1 and N equal to 2. When N equal to 1, IS is equal to what? 10 to the power minus 3, which is 1 milliamp, multiplied by E to the power V, which is in this case 0.7 volt, 700, divided by 25, okay, which is this one here, right? Okay, and that will give you IS is equal to 10 to the power 15 amp, okay, or sometimes we call it 15 femtoamp, okay, 15 femtoamp, okay. Now, if I use N equal 2, I will substitute here for N equal to 2, and that will give me what 10 to the power minus 3 e to the power minus 700 divided by 50, okay, because I multiply by 2, and that will give you what, approximately 10 to the power minus 9, or we call it nanoamp, okay? So when N is equal to 1, the current is femtoamp. When N is equal to 2, the current will be nano. So the difference between them is about 1,000, okay? It's more than 1,000. It's about what? 1 million, right? 1 million. Okay. All right. Excuse me. Can you switch your microphone off, please? Thank you. Okay, guys. All right. Now, so the difference between what, a million, right? Okay. Now back to our question here. He said, what scaling constants would apply for 1 amp diode of the same manufacturer that conducts 1 amp at 0.7. Okay, I is equal to 1 amp. So take 1 amp and substitute it in here. Okay, instead of milliamp, and you will find that for N is equal to 1 and I is equal to 1 amps, Is is equal to 10 to the power 12. Okay, which is pico amp. Is now become pico instead of femto. Okay, so a reduction of 1,000. Okay, or increase of 1,000. And for N equal to 2 for the same value, Is will be 10 to the power 6 or nano. Okay, so by just changing, N, there is a dramatic, change between Is equal when N is equal to 1 and Is when equal to 2. Okay, the difference between them is about 1 million. Okay, 1 million. 10 to the power 6, right? All right. Any questions? Questions? Okay. Effective of temperature on semiconductor diode. If the diode say, this is the graph, okay, which is the curve for ID versus VD. If the temperature here say 25 C, okay, and you will see that this is here VD is equal to 0.7 volt. As the temperature increase, as I said here, okay, the voltage drop decreases by approximately 2 millivolt for every 1 degree increase in temperature. Well, this is, hey guys, this is approximate, okay? This is approximate. So that's mean, if the temperature increases from T is equal, say, for example, 25 to 25, okay, to T is equal to, say, 26, see? Okay, then the voltage here will be shifted to the left, okay, and this one here probably instead of 0.7 will be 0.5 volt. Got it? As you increase the temperature, the graph will be shifted to the left. Okay. All right. Slide number 27. This is an example for iteration. Just go over it, guys, and see how if you have a question. Okay, it's very simple. All right. Now this one here on slide number 30. This is example 2. Okay, this is current in semiconductor diode. Okay. And why did I put this example here? It's because this one came in one of the exams, okay, in the previous years. So that's why I put it here. Okay, so I am giving you guys a revision. Okay, guys, I'm giving you a revision as well. So as we go through the materials, okay, I throw a couple of examples that came from previous exams. Okay, guys. All right. Is there any question before we start? All right. For example 2 here, for the circuit shown, set D1 and D2 are identical, means they are the same. Okay, having N is equal to 1. Okay, and Is is equal to 10 to the power minus 14 amp. Okay, find the voltage drop across each diode. You want us to find the second voltage drop across D1 and D2. Okay, and the current I. What is I? This I here. Okay, so that the voltage V, what is V over here? Everybody see V? Is equal to 0.1 volts. Okay, he gave us, VT is equal to 25 millivolt. Okay, 25 millivolt. Okay, guys. Now what we now look at the circuit, okay, and you can see that there is a node here. Okay, there's a node. Okay, and when you have a node, according to Eeng261, okay, chapter 2, you can apply KCL. Okay, KCL, and therefore, you know, KCL said I is equal to ID1 plus ID2. Everybody said that? Everybody see that? Okay. Now I want to calculate VD2. Okay, VD2, which is across the D1, first of all. Now I can't do that until I have a current ID. Okay, I want to find the ID2. What is ID2? ID2, I have it here, flowing here, right? Remember that I can take KVL like that, okay? And that will give me what? Will give me what? Will give me what? Minus 0.7, okay? And plus ID2 multiplied by 10K, okay? Minus 5 is equal to 0. And therefore, you know, this will be what? ID2 will be equal to 0.1 plus 5 divided by 10K, and that will give you 0.51 milliamp. Okay, easy, easy. Okay, now, is there any questions? Now I found the current flowing through the D2. I can find VD2, right? I use this formula. Okay, ID2 is equal to IS e to the power of VD divided by NVT. Okay, can I do that? Yeah, I can. And then I can solve for VD. How? This is how. VD2 is equal to NVT ln ID2 divided by IS. Okay, do I have IS? Yes, I do. Okay, and I have ID2 and I have VT and then N. Okay, substitute, okay, and I will find that VD2 is equal to 0.616 volt. So the voltage drop across this is 0.616 volt. Everybody see that? Any questions? Okay. Okay, now I found the current here. I found the voltage here. Okay. Can I find the current ID1? Can I find the current ID1? No, because because I don't have the value of I, so I can't, right? Okay, now I'm going to redraw the circuit again. Okay, redraw the circuit. But before I redraw the circuit, okay, I said, you know what? Let me take my voltmeter and measure the voltage over here, V. So how am I going to measure it? I take my voltmeter, dial it to VDC, okay, over here, and then put the red on the V. And usually when you want to measure a voltage, you measure it with respect to ground. Okay, got it? Everybody get that? When you measure a voltage, you measure it with respect to ground. Okay, so you measure it with respect to ground. I measure it with respect to ground, and I found it is equal to, of course, I would say, oh, wow, exactly 0.1 volt. So my voltmeter will say 0.1 volt. Very good. Okay, now I use this ground over here. Hey guys, but also there is a ground here, the same ground. So that means if I put my voltmeter between here and here, I will measure 0.1 volt. Everybody get that? So now I'm going to redraw the circuit. Okay, and then I will replace this diode by their equivalent model. Okay, that's on slide number 31st. Okay, now this is the same circuit here. Okay, 5, Okay, this is 5K, and this is VD1, okay, and this is VD2, and this is here 0.1 volt, okay. Remember, this is 0.1 volt, this is VD2, which is 0.616, right? 0.616, we calculated it. Therefore, VD2 is equal to what? Is equal to this voltage plus this voltage. And that will give you 0.716 volt. Okay? The voltage across V2 will be equal to 0.7616 volt. Okay? So VD1 is equal to 0.716 volt. Okay, now I find the voltage. Can I calculate the current? I can calculate the current using ID1 is equal to IS e to the power VD1 divided by NVT. Okay, substitute for the value of VD1, N, and VT, and I'll find that ID1 is equal to 0.027 amps. Okay. Okay, now I can take that and substitute it for ID1 and ID2 and solve for I, okay, using this is KCL, and I will find that I is equal to 0.51 milliamp plus 0.027 amp, and that will give you 0.0275 amps. Okay, any questions? All right. Everybody understand? Okay, the same thing here. Okay, this came also, in one of the exams before, long time ago. Okay. Okay, he said determine the value of R. He wants us to find the value of R. Okay. He said, that the diodes are identicals. Okay. Conducting at 10 milliamp at 0.7 volt. Okay. And he gave us NVT is equal to 25 millivolt, which means that N is equal to 1. Okay, and V out, he said, equal to 800 millivolt. Okay, 800 millivolt. And so he wants us to calculate the value of R. Okay, so to calculate the value of R, we need the current ID2. Okay, and we need the voltage here of D2. Okay, across D2. Okay, but before we do that, we want to use this formula that we just took. ID is equal to IS e to the power VD divided by NVT. Okay, NVT. All right, and we're going to solve for IS. Solve for IS. Okay, substitute for the value of 10 milliamp, 0.7, and 25 millivolt. Okay, solve for IS, and IS is equal to 6.915 10 to the power minus 15 amp. Okay, or femtoamp. Now I can calculate ID1, right? Can I calculate? I cannot calculate ID2 yet. Okay, not yet, because I didn't have the current here. I can calculate the current ID1, and the current ID1 is equal to, well, I substitute in this here, ID is equal to IS e to the power VD should be VD divided by NVT. Okay, now here's a question for you. V out is what? 800, okay, millivolt, or 0.8 volt. Okay, now if I put my voltmeter between here and ground, I will measure 0.8 volt. Where is it? Where is it also? This voltage also seen by this diode. So the 0.8 volts also across the diode. Therefore, VD2 is 0.8 volt. Substitute an ID in this formula here, and you will solve for ID1, and ID1 is equal to 0.546 amp. Got it? All right. I have a KCL here. I mean a node. So I apply KCL. I have one amp and I have 0.546 for ID1. I can calculate ID2. And ID2 is equal to 0.454, okay, amp. Okay. I found this current here that's flowing through the diode here and through the resistor. I can find the voltage across the diode number 2. Okay. Using what? Using VD is equal to what? Is equal to NVT ln. Okay. ID. Okay. ID2 divided by IS, where IS is this one here. Okay, solve, and you will find that VD2 is equal to 0.7954 volt. Okay, 0.795 volt. Okay. All right. Okay. So the voltage drop across here is what? Is the voltage here minus the voltage drop here, okay, divided by the current flowing. And that will give you 0.01 ohms. 0.01 ohms. Any questions? Any questions, guys? Questions? All right. Everybody understand? Okay. Next. Okay. This is the same same thing. Okay. You have I2. You have I1. Okay. The same thing. Go over it. And if you have a question, let me know. I mean, it's the same thing as what we just solved. Okay, see? Same. All right. Okay. Slide number 35. Okay. Slide number 35. This is diode equivalent circuit. And we have seen this before. Okay. We have seen. I'm just repeating it again. Now we want to see, okay, we want to see exact model, okay, or similar, approximate model that is going to be close to the normal characteristic curve of the diode. Okay, remember this is the diode, this is the anode, this is the cathode, this is SI, for example. Okay, now as we said before, we can replace this diode with its equivalent model like this, which is a little bit of a small battery like that, which is equal to VD equal to 0.7. Why? Because it's a silicon diode. If it is a germanium, will be what, 0.3, and if it is a gallium arsenide, it will be 1.2. Okay, the graph of it, as we said before, since it is 0.7 volt, it will be like this. You have to exceed 0.7 volt in order for the diode to be forward bias. Once you reach 0.7, the diode will go, okay, on, okay, forward bias. Okay, guys. Now, is this exactly, or approximate exactly the same as the normal diode? Well, not really, not quite. Why? Because the diode curve should be like this, exponential like that. Okay, something like that. It's not like, okay. Okay, now slide number 36. Okay. This diode, okay, that we did here, okay, is what? Is actually, ideal diode plus the VD 0.7 volt. This is exactly the same, right? Okay. So this is ideal diode actually, and and 0.7 volt. Okay. And that's why this is 0.7 volt. But still, we still have, we didn't know how we're going to do, exponential here. Okay. Now, the diode actually, the real diode is like this, yeah, with the black. This is the black curve of a diode. okay? And the one that we approximate is straight. So how are we going to make this curve to be as close as possible to the normal diode, okay, to the real diode? How are we going to do it? We have to bend it a little bit. How are we going to bend it? Well, instead of to bend it, we have to add a resistor to it, okay, to the diode. So it will be like this. When we add a resistor, the slope of the curve, approximate curve, will be like this. And this is very close to the real curve, okay, as you can see. And the resistor will be very small, okay? And now the curve has a slope of 1 over RD, okay? 1 over RD. All right, okay? As you can see, now the whole model for the diode will be ideal diode, okay? VD, okay? And a little bit of resistor, okay, called RD. Okay, so between here and here this is what represent VD, which is equal to 0.7 volt. Okay, and you will get the slope like that. All right. Any questions? Okay. Okay, no questions at all? Okay. Very good. Slide number 40. Okay. We're going to look at the graphical analysis, okay, using exponential model, okay, using the exponential forward bias, okay. Okay, now suppose, okay, I look at for example, silicon diode. Okay, this is the curve for silicon diode, for example, okay, and I can see that the curve this is the real diode, exponential like that, okay, and this curve here is drawn by this ID, excuse me, ID is equal to IS e to the power VD over NV VT, okay? And if I take that, the diode, and put it in a circuit like this, I get VDD connected to R, and then connected to a diode. Hey, you guys, one thing I want you to remember is that try not to connect the voltage supply directly to the diode, okay? Because if you do that, okay, there is a chance that you will burn it, or okay, especially in this case here, if you do that, the diode will conduct and will be, for example, short. And when it is short, the VDD will be drained out, okay? So don't connect the voltage directly to VD, to the diode. You have to put a limiting resistor called R, okay, R. And that's why, you know, when you want to connect, say, a diode LED, okay, when you want to connect LED, for example, this is the LED, and what you do is you put, this is the VDD or VS, okay, supply voltage, VS, okay, and you want to connect a diode, okay, for the this is for the LED, okay, LED, okay, and it has a symbol like this. That's for LED. If you connect it directly to the supply voltage, okay, there will be huge current flowing through it, right? and therefore, because of that huge current, the diode will burn. Okay, your LED will go off, and we'll say, oh, what happened? It's because you didn't put a limiting resistor. Okay, so you have to put a limiting resistor R. Okay, a small resistor, so for example, 390. Okay, 390 ohm. Okay, or 330 ohms. Okay, so this is a limiting resistor. Okay, so when you do that, there is a current here, flowing called ID, and there is a VD, which is about approximately 0.7 volt for the silicon diode. And therefore, if you want to calculate ID, you take KVL, okay, minus VDD plus ID, IDRR plus VD is equal to 0. If you're going to solve for ID, it will give you this. ID is equal to VDD minus VD divided by R. Okay? Everybody got that? All right. Now, what happened is that in the past, long time ago, when they first created the diode, okay, they look at the curve, which is this one here, exponential curve, and they say, wow, the curve has slope. Okay, the curve is not straight, the curve has slope. And they said, wow, every time they see something like this slope, they will say, well, it can amplify a signal. Okay, we can use it for amplifier. Okay, we can use it for amplifier. Okay, now, hey, you guys, what is an amplifier? Anybody? Amplifier is a device, okay, that will take a small signal at the input, very small signal, say in milliamp, microamp, and then it will make it big, huge, okay? It will make it in volts, got it? At the output. So you take signal at the input and you amplify it, and then you will get a big signal at the output, okay? Big voltage at the output, okay? Why do we have to do that? Why? It's because your the speakers, okay, okay, they operate in volts, okay, they operate in volts, got it? And when you receive a signal, say, and from Tokyo, from Europe, from America, from South America, if you receive it, you have antenna and you receive it, you can see that the signal, okay, very, 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 very small. It's approximately, in millivolt or sometime in microvolt. So you cannot take that signal and put it to the speaker and you expect to hear something. You won't. Okay, you won't. So what you're going to do, you have to amplify the signal. Make the signal from micro or millivolt to volt. So when you make it volt, you can put it to your speaker and you can hear somebody say hi or help or something like that. Got it? Okay. All right. Any questions? We'll get into that more detail when we go to the real amplifier, okay, that we designed from transistor. Okay, you will take it, in this class, okay, and you will take it in Eeng262 and so on. Okay, powerful amplifier. Everybody get that? Okay. All right. Now, so what we're going to do? Yeah, what we're going to do is this. Oops. We're going to take this, okay, the curve here, and we say, you know what? Let's choose a point where we're going to operate, okay, where we're going to put our signal, okay, at the input, okay, and we chose, for example, this point here on the graph, this point, for example, okay. And when we choose this point, we call this point, this is the point where we're going to operate at. Okay, this is the point where we're going to apply our signal. Okay, we're going to apply our signal at this point. And we call this point operating point. Okay, what do we call it? Operating point. Or sometimes we call, most of the time you will see it Q point. They call it Q point or operating point. What does Q point stand for? Q point means quiescent point. Okay, quiescent. What does that mean? It means that at this point, your amplifier is quiet, very quiet. Got it? We'll get into that in more detail. So your amplifier at this point is quiet. Okay, very quiet. Okay, and your Q point usually or all the time is formed by DC, IDC and VDC. Okay, IDC and VDC. Okay, that's how you choose your point. Now to choose to make sure that you have chosen this point, okay, you draw a load line that will intersect the curve of the diode at this point. Okay, at this point, and we call this line. This is straight. We call this line a load line. What do you call it? A load line. As you can see, this is a load line. Okay. When we do that, okay, we look at this point, and this is our operating point, and we look at we can look on the y-axis, and we'll see ID. We look at the x-axis, and we see VD. Okay, now how do we define? How do we draw this line? How do we draw it? This line could be drawn this way, okay, that way, okay, so many. Okay, how do you find these two lines? We need to define these two lines in order to draw the load line. Okay. Okay, now to find this point over here, which, okay, we find it. We come to our equation here, the one that we produce from here. Okay, and we said that at this point, we look back over here, and we say that the ID is equal to 0. So when ID is equal to 0, okay, when ID is equal to 0, VDD is equal to VD. Okay, VDD is equal to VD. So this one here, VDD is equal to VD. Okay, or VD is equal to VDD. Okay, and if your VDD is equal to 10 volt, this point is at 10 volt. Okay, so you identify this point. Now, how are you going to identify this point? To identify this point, okay, you look back, okay, at the origin, and you will see that VD, which is this one here, is equal to 0. Okay, so when VD is equal to 0, ID is equal to VDD divided by R. Okay, got it? Everybody get that? All right, and then once you define these two lines, you take a ruler, put it between these two lines, and draw straight line until it intersect with the operating point. Okay, so how does it amplify the signal? That's in here. Okay, so what we're going to do? Okay, we have a resistor here, of course, right? We have the circuit. What we do is we take our signal. This is the signal. This is the AC signal. Okay, AC, which is coming from Tokyo, Mars, the moon. Okay, we have spaceship. on the moon, sending signal. Okay, and this is the AC signal, and this one here is the DC. Okay, DC, and we put it like this. Now, what happens is when you do that, we have operating point. Our operating point, our load line is coming like this. Okay, and intersect the curve in here. Okay, on this point. So we call this Q point. Okay, right now, VD is equal to 0.7 volt over here, which is this one here. Okay, so now the AC signal, for example, say it has a triangular waveform. So you put the triangular waveform here, okay, which is coming from this here, which is approximately in millivolt, and then take this one up until hit the curve on 2 points, and then you can see that it will produce the same voltage, except it is bigger. The same waveform, except it is bigger. This is what? This is in milliamp. Okay, this is in milliamp. So you take that, put it through a resistor, and you will get volts. And then from there, you take it to your speaker, and you can hear something. So actually, ID, which is this one here, ID, this is the total. This is not DC, guys. This is the total, ID total, okay? ID total is equal to ID DC plus ID AC. Got it? So these are the total. Okay, more about this when we go to and study transistor amplifiers. Okay, guys? Any questions? Questions, okay. So as you can see from 42, ID is equal to ID plus 1 plus VD, which is this is the AC, divided by VT, which is the thermal. And this is what ID total is equal to ID DC plus ID AC, okay? Where ID AC is equal to this multiplied by this here, okay? All right. You can go and solve example 4.5 and 186, page 186. This is your soft copy. Okay, or if you have hard copy, it will be on 176. Sidran Smith. Okay. All right. Any questions so far? Any questions? Any questions, guys? Okay.
No questions.
No questions? Good. Another application for your diode is mentioned on slide number 43. Okay, that's another application for the diode. Okay, another application for the diode is on slide number 43. Okay, what do we use it for? Okay, we use the diode as a voltage regulator. Okay, as a voltage regulator, and a voltage regulator, okay, is a circuit whose purpose is to provide a constant DC voltage between its output terminal. Okay, in spite of changes in the load current drawn by the regulator output terminals, and in spite of changes in the DC power supply voltage that feeds the regulator circuit. Okay, so over here I have this circuit here. This is represent a regulator. You said, what is this? How does it do that? Well, this is a regulator actually. Okay, now here's what I'm going to say. Okay, suppose I have do I have, yeah, there you go. Okay, suppose this is slide number 44. I have VCC here, and then I connect VCC to 1K ohm, And then over here, this is my output. Okay. I think, I put many of them. Okay, let me go back. Let me do this. Do it again. Let's do it again. Okay. All right. Let's do this again. Okay, suppose I have a voltage supply. Okay, say VCC. Okay, and it's equal to say 10 volt. Everybody see that? Okay. Now what I'm going to do, I'm going to do this. Okay, I connect a resistor. Okay, 1K ohm. Okay, and then I come here. This is V out. Okay, and then I come here and I put a diode. Okay, a diode. This is what? SI. Okay, SI. So when I put the SI for a diode, any diode, if I put SI, that means it is silicon diode. Okay, which means that I'm going to drop what? What's the voltage?
0.7.
0.7 volt. Okay, and then go like that. Okay, now, okay, so now what happens that, because this is 10 volt, and over here will be weak 10 volt, the diode will conduct, that means it will be forward bias. When it is forward bias, okay, what is V out equal to, guys? What is V out? Anybody? If I put my voltmeter, guys, over here, okay, if I put my voltmeter over here, okay, this is my voltmeter. Okay, I put the red lead over here and the black one over here. My voltmeter will read V out equal to what, guys? Anybody? Come on, guys. What? Is this on or off? Forward bias or reverse bias?
Forward.
Forward bias. Okay, so when a forward bias, okay, this one will be replaced by?
Short.
This is short, this is silicon. Okay, this is not ideal. Ideal will be short circuit, right? You are right. But this is silicon, guys, silicon. So therefore, I will replace it with? I will replace it with? Okay, I will replace it with? The model.
Right.
So my voltmeter will read what, guys? My voltmeter will read?
0.7.
Will read 0.7, very good. 0.7 volt. Everybody get that? Okay. My 0.7 volt. If I take another one, okay, if I take another one, okay, if I take another one, let me take another one here. If I take another one, oops, whoa. If I take another one, let me draw this one again. Okay. Okay, if I take another one, so this one here will be 1 over here. And then I go and take another one, the same thing, and put it over here. Okay. These are both SI. So my output voltage will be equal to
1.4.
1.4. Thank you very much. So now Now this one here will be 1.4. Okay, 1.4. Got it? So this one here will be 1.4. Okay, 1.4 volt. Okay, now back to slide number 44. Now if I put 1, 2, 3, 4, what is my output will be? Will be 2.8 volts, right? Because 0.7 multiplied by 4 is equal to 2.8 volt. Okay, now just suppose, my VCC is 10 volt, right? But it's not smooth VCC. Okay, it has some kind of noise, and noise, it will go like this from 10 volt to 7 volt to 6 volt. It goes like this. It's not a clean. It's not a clean VCC. Okay, it's not a clean VCC. Okay, however, my V out will not see this, right? Will not see this, right? It will see, my V out will see clean, okay, 2.7, okay? And that's why, because it's clean, which means, okay, I am regulating the output V out at 2.8 volt. So your 2.8 volt is clean, okay? That's called regulation. Okay, guys? We call it what? Regulation. Everybody got that? Okay? All right. Even if this one here goes to 5 volt, from 10 volt to 5 volt, okay, noise, my output will be 2.8 volt. Okay? And you can actually multiply this, put more and more and more and more until you get, say, for example, 5 volt. If you want 5 volt study, you will get 5 volt by adding more diodes. Okay, we call this regulation. Okay, now this is a crude way of doing it. Okay, later on we're going to replace these diodes by a diode called Zener diode. Okay, replace everything by Zener diode, and that's coming in the future slides. Is there any question? We reach 44 here. Okay, any questions? We stop. We should stop here. Okay. Any question, guys? Any questions?
No questions.
No questions? Okay. Very good. Okay. Don't save. Okay, there's no questions. Okay, we're going to stop recording.